Bismillah ar-Rahman ar-Rahim. Uh, the students were facing a problem to how to construct a efficient frontier using the Markowitz approach. Today, inshallah, we will be going through this session, and we will be first. This session is in two parts. The first part covers the theory part, and the second is related with the Excel. Uh, so, what is an efficient frontier? Efficient frontier is basically uh, this is an efficient frontier. This is an efficient frontier till y. The rest is not an efficient frontier till this is the efficient frontier where for a given level of risk you optimize your return. For a given level of risk you optimize your return, or for a given level of return you minimize your risk. This is that point. Over here we've got the unattainable set, and below the efficient frontier is the attainable set, but the points over here are known as inefficient points, and the points on this axis on this in the curve is known as the efficient points. And all points, whether it's we can say this A, we can say this point as B, this point C and point D, all points are equal, because over here we are minimizing the risk for this level of return, or we are for this level of return we are minimizing the risk, or for this level of risk we are maximizing the return. And same for it, the other stands for it. Though over here if the risk is more, then the return is also more. If the risk is more, the return is more. At point D the risk is more but the return also. That means there is a positive relationship between risk and return. What do you mean by uh, uh, that for a given level of risk we optimize or maximize our return? Look, if you say this is a for a given level of risk, this is for risk, we call it, for example, 5%. 5% standard deviation is there. Now we get different returns for if you draw a line perpendicular to x-axis. So there are different points on it. The point above this line, like this point or this point, is in the unattainable phase. But point below C, there are many points, innumerable points. You get different levels of returns over here. The maximum return you get at point C is this. You can't get more. If you move away above C, like this point, like we call it E, so this is in the unattainable part. This is not possible. So the point C is the for a given level of risk we get the maximum return over here. The returns below the C line are less than the returns given at the point C. Likewise, if you draw a perpendicular line from the y-axis and we make it like this, so there are this part is known as the unattainable point. That is not possible. Then from point A onwards, if you draw a line, the line keeps on going. There are different points on this line. This line might not be straight, it's not straight, but is basically a straight line. There are different points. So for this level of return, you can get this much risk also, this much also, this much also. But at this point, that point A is the minimum risk you get for this level of return. Away, if you move more towards the left, is the point, for example, F. You can't get any. You can't get this point because this is in the unattainable side. So for a given level of return, we are minimizing our return. So this is what efficient frontier is. Now point A, B, and C and D are all equal. There is no difference. And the last point is this V over here. This is the global minimum variance point, where if you draw a line perpendicular, draw a line perpendicular, a tangent point over here, this line is parallel to your y-axis. That means it's got a slope of 1 by 0. That's almost infinity. That's infinity. So this is that point where if you draw at a tangent point, the tangent line is parallel to y-axis. Below this point, eventually the the curves come back, and if you observe, if you draw a line from here, there are two points over here. We call it G, for example, and we call it A. Now, what is happening for a given level of risk? We are getting G also, that is return at G, and return on B. A, sorry. So the return on A, the return at A is more than G, so we don't need this side of the line, because this is the inefficient part. This is the attainable part, but the inefficient part. So we are only left with this line also. And same goes over here when it comes to turn like this. So if you draw a line perpendicular to this line and it crosses over here, so this point and this point are not equal, because for a given level of return over here the risk is less as compared to the point over here. So again, this is a inefficient line. So we are left with only this point, and this is the efficient frontier. So this is a very important contribution given by us, by the Markowitz, where for a given level of risk we maximize return, or for a given level of return we try to minimize the risk. And this line helps us to identify what will be our priorities, investment priorities, where we want to invest. Then the financing priorities, or the separation theorem, the investment is separated from your preference decision. Over here, no preference has been made. Only on the basis of the data we've got, we construct an efficient frontier, that is in which investment to invest. Nobody says what my priority is. The priority comes from the difference curves. There are innumerable difference curves over here, and where they get touches the efficient point as a tangent point. If you draw a tangent point from here, it will touch at one point. I'll draw more. It will be like this, like this, like this. So it will touch the efficient frontier. For example, over here at one point, that will be the combination of your investment decision and your preference decision. If I would say, if the investor is less risk averse, then the person will select this area, and if the person is more risk averse, the person will select this part of the efficient frontier. If the person lies in between these two type of person, the person is more probably will be lying over here. Okay, this is but basically what efficient frontier is. Now coming to the efficient frontier, so we will be going for the 2 asset portfolio case, then we will go for 5 or and cases. You can do it for yourself, 10, 20, whatever do you want to. So this is what Markowitz did. Basically, if you remember, we went for the 4 moments, and we said the stock returns are normally distributed. When they are normally distributed, that means that both the tails are equal, and then skewness becomes 0, and kurtosis becomes insignificant. It is so we are only left with 2 moments. What is the mean, and the second is the variance. So we basically, if you remember, in the class we discussed that we appraise our decision on the basis of 2 parameters, that is risk and return. The proxy for return is mu, that is return, mean return, and the proxy for risk is your covariance, is your risk, that is the standard deviation. Markowitz said that basically, if you want to make a decision, you have to be dependent on 2 parameters. One is the return, and the second is the covariances. The covariances, when it is the covariance is with itself, that is I if the covariance is with itself, it becomes variance, and if it's with other securities, is known as covariance. So basically, this is also a sort of a covariance. It's a sort of a covariance, and this is not rather as a sort of a, it's a covariance, but is a covariance with the term itself, and we call it variance in stats. And to Marquardt sets, this is the contribution given in portfolio theory. We used to focus on this thing also, that the investment was appraised on the return and the variances only. There were no covariance part over here. But Marquardt said that we have to appraise on the covariances, and the covariances, it is not only variance, the covariances itself is the variance, and the ij will be the technically what we call it covariance. So what will happen? This becomes your ultimately what was the outcome of Marquardt's proposition, that we have got two type of risk: non-diversifiable risk and non-diversifiable risk. So this is your non-diversifiable risk, and this is your that means as you keep on increasing the number of securities in this in a portfolio, what will happen? The risk over here, this part of the risk will eventually be eliminated, will be mitigated. But this part of the risk would be like this, going up and down, but it will never get mitigated. It will have it will stand at some level. And when you draw a line, it is something like this. If you draw a line over here, we write the number of securities in a portfolio, and we have the standard deviation on the y-axis. So the line comes dropping like this, and this is your non-diversifiable risk, and this is your diversifiable risk. That means this comes from here, and this risk will be always, it comes from here. Okay, so this is what Marquardt's equation was. And when we are optimizing, we are constructing efficient frontier. So what we are doing, we are minimizing the return for a return, and the second constraint, there are two constraints. One is the return, the second is all weights are equivalent to 1. This is a very simple why all weights are equivalent to 1. That means they have to be up to the level of investments. Or we can also do the other way, say we can maximize the return for and put this equation in the constraint area, and we again get two constraints. One is the all weights equivalent to 1, and the risk will be defined in this way. But this has got a big problem, because we have got a linear equation. This is a linear equation. Its value is 1, 1. The power is 1 and 1. This is a linear equation. We are optimizing a linear equation, and with a quadratic, you know, this is the quadratic equation because it's got powers over here. So we are optimizing a linear equation with a quadratic constraint. That's the software perhaps won't give a good feasible solution over it. The easier way is minimize a quadratic equation with linear constraint. This is a linear constraint, this is a linear constraint. So this is easier as compared to the other way around. So normally what we do, we normally follow this procedure. We optimize the risk, that is minimizing the risk, that is quadratic in nature, with linear constraints. Okay, inshallah you'll understand. So this is what efficient frontier will be. For n cases, I've made a general case out of it. You keep on adding the assets. This is the sigma part, you add them, and it's a double summation because we've got two parts. If you remember, the equation was like 2 into x1, x2, and covariance of 1, 2. Actually, this equation was like this: x1, x2, and covariance of 1, 2, plus there was another term x2, x1, and covariance of 2, 1. Now what happens when it is, we say that it's normal distribution. So what happens? X1, sigma 1, 2 is equivalent to sigma 2 1. They are equal. So they become equal, and x multiply x1 into x2 or x2 into x1, it does not make any difference. 2 into 3 or 3 into 2, the product is always 6. So these terms become equal. When we add them together, it becomes 2. So 2, and when we are generalizing it to this double summation actually represents, we are summing twice. 1 x1 x2 summation 1 2, x2 x1 summation 2 1. x1 x3, for example, is a 3 asset case. 1 and 3 1 3, 3 and 1 3 1, 1 2 and 3 2 3, 2 3 and 2 and 3 and 2. So this is, so double summation means you will be adding twice, and this is the matrix operation. Why we are using this is because it makes us easier to optimize the matrix operations. Using the matrix operation, it is very easy. This formula and this formula is the same. There is no difference. This is a row matrix. This is a row matrix. This is a column matrix. Row matrix is like this. There is one column and there are many rows into it. And when we take a transpose, it becomes a column matrix where there is one row and many columns. So this is basically a row matrix. This is the row matrix, and this is the column matrix, and this is the covariance matrix, that is basically n by n. It's a square matrix where your number of rows is equivalent to number of columns. There are 2 rows and there are 2 columns. There are 3 rows, there are 3 columns. There are n rows, there are n columns. It's an n by n matrix. So this is, we will be using this thing in our when we are running the Excel. This thing makes things simpler. When we've got, for example, 100 assets, we want to optimize it. It is very difficult to write this formula for 100 assets. That means for 100 assets, we have to calculate how many covariances, n into n minus. That is 100 minus 1. That is how many covariances? 9,900. Yes, that's too much. For example, if you've got 5 assets, then you have to calculate how many covariances? 20. Then 20 is, you might be missing many of the variances. So for 100 asset case, this formula, using this formula without using any sort of a software or program, it's very difficult. So rather than using this formula, we use this thing. Now you take an assignment how this thing is equivalent. You can do it yourself and then present it to me as as part of your assignment. So what will be the steps in constructing the efficient frontier? First of all, you have to down the stock prices of different companies. Then you have to convert those stock prices into return, because we use return, not prices. This basically help us calibrating all the companies together. When we are using stock, for example, a company stock is in 1000, is running in 1000, another company stock is running in 100s, and the third is running in tenths. So you can't calibrate them. When we are in returns, it is very easy. We can use both of the formulas, log returns, log difference returns, and we can use the P2 minus P1 and divide by P1. This is a very simple formula, but I prefer this because this helps in calculating the returns also, and plus it smoothens the returns also. Normally there is a noise when you are using this this formula. This formula, the log returns formula, tends to smoothen the noise in it. When the noise is low, that there is a high possibility of the accuracy. Then you have to calculate for each company their average returns and standard deviation and the variances also, and the covariance, and construct the covariance matrix. Then if you are not optimizing, use an Excel solver or any tool, just put some arbitrary weights, any weights you want to take. For a 2 asset case, I'm saying. For a 3, 4, 5 asset is a very difficult. So for 2 we'll take some arbitrary rates, and when we are using the optimizing tool, thus we will be constructing the weight matrix, because then we will outline the constraints. There are 2 constraints. One is the portfolio return, and the second is the all weights are equivalent to 1. There is another constraint also that can be given over here. That is, over here I did not say the short sales were allowed or not. When these two constraints are given, that means short sales are allowed. But if I give a constraint like this, the all weights be equivalent to will be more than 0. That means short sales not allowed. Short sales not allowed. So what is the impact of the short sales? If we go back, if I construct an efficient frontier, this will be efficient frontier with short sales not allowed, and this will be an efficient frontier with short sales allowed. Over here till this point, the efficient frontier are more or less the same. But if we move more, we add more risk or more return to it, so there will be a differences. This part will be coming. This is basically short sales not allowed, and this is where short sales allowed. So what is happening? Okay, for the same level of risk, over here we are getting low return as compared to short sales allowed. So when we allow short sale, there is a probability which will be expected rate of return will go up. Okay. So for simplicity say, we are not getting into the short sales, but we will put we can put that thing as a constraint also, no? And then calculate the portfolio risk and return for each point. There will be different points in it. Then you and then just you plot those point and link them. It becomes an efficient frontier. This is all for today, for this first part of the session, and the second part will be we will be following these steps to construct an efficient frontier in Excel. Jazakumullah khair.